Hello everybody, and welcome to your second installment of Not Your Professor, your one-stop shop for everything from mitosis to MDMA. We explain science in a way that makes it stick, factual, concise, and explicit. We post weekly videos tailored to a variety of different scientific topics to help students learn and retain information in a way professors simply cannot. Bring your smelling salts, join the wave, and subscribe. Now that we got all the fun out of the way last week, it's time to discuss some of the more specific garbage that needs our attention. Yes, for those of you who are getting all horned up to hear my voice each week, this is all going to build up to proteins. For now, however, we've got to stick with the more basic amino acid bullshit, because all this information is going to stick with you for the rest of your lives and be used almost daily. Okay, fuck that. Let's just get started. I already know most of you aren't going to retain more than 10% of this, so let's just get going. For our first example, let's go easy and use alanine. Amino acids are amphoteric species. That word sounds like a bear, but that's just the way scientists decide to describe species that it can accept or donate a proton. Acid-base chemistry is important for this, so go back and review that shit if you must, because we are saving that lesson for a completely different day. Under basic conditions, ionizable groups tend to lose protons, then likewise gain them under acidic conditions. The pKa of a group took me forever to grasp, and honestly, I still barely know what I'm talking about, so bear with me. It's basically the pH at which half of the molecules of that specific species are deprotonated. Confused? Yeah, well, this isn't Miss Snyder's third grade noodle art bullshit, so pay attention. Alanine has a pKa for the carboxyl group of 2.34. If the pH is greater than the pKa, then the majority of the amino acids will be deprotonated. However, if the pH is less than the pKa, the majority will be protonated. Again, for my chemically challenged friends, the lower the pH of solution, the more acidic the solution, and the more protons that will be present in the solution. Alright, that was a mouthful. And if you think that's bad, well, I got news for you, bub. Each amino acid has at least 2 pKa's. Why, you might ask? The first is for the carboxyl group, and the second is for the amino group. Then there are the amino acids that have another due to their side chain. Just when you think you get a break, you get hit with a swift punch to the gut. Amino acids are a lot like handjobs. You know where you're getting, and you're still disappointed afterwards. One thing to recognize is that once an amino acid loses one of its protons, it still exists at a neutral charge. Alanine's first pKa of the amino acid is 2.34 for the carboxyl group, and its second is 9.69 for the amino group. Nice. When the amino acid is present at a pH of 5, the carboxyl group will... Alright, that was a mouthful. And if you think that's bad, well, I got news for you, bub. Each amino acid has at least 2 pKa's. Why, you might ask? The first is for the carboxyl group, and the second is for the amino group. Then there are the amino acids that have another due to their side chain. Just when you think you get a break, you get hit with a swift punch to the gut. Amino acids are a lot like handjobs. You know where you're getting, and you're still disappointed afterwards. One thing to recognize is that once an amino acid loses one of its protons, it still exists at a neutral charge. Alanine's first pKa of the amino acid is 2.34 for the carboxyl group, and its second is 9.69 for the amino group. Nice. When the amino acid is present at a pH of 5, the carboxyl group will be deprotonated, aka negative, and the amino group will remain protonated and positive, thus canceling each other out and maintaining an overall neutral charge. This molecule is called a zwitterion, not the word I would have chosen, but it's distinct, like when you catch a whiff of body axe walking through the bar. And similarly douchey too. The easiest way to look into these actually work is to examine them via titrations, unfortunately. Now, if you have taken chemistry 2, then you have already suffered through a minimum of 3 lessons of these. And if you haven't, I would start clenching, because you're about to get fucked. Now, the overall goal with titrating amino acids is to find the isoelectric point, much easier word to manage, which is the pH at which a molecule is electrically neutral. So let's examine glycine, because everybody loves some glycine. At a low pH, it will exist primarily in its fully protonated form, thus positive. If a strong base were to be added to the titration, the carboxyl group would begin to deprotonate. The pH where its fully protonated form equals its neutral form, or its zwitterion form, told you fuckers I would come back, is the pKa1 equivalent point. Considering I know most of you slacked off during chemistry class, when pH is almost equal to pKa, the solution acts as a buffer and resists large changes in pH unless large amounts of base or acid are added. Now, the isoelectric point formula is as easy as you're going to see. Like, not even worth writing on the back of your hand easy. Simply take the pKa of the amine group and the pKa of the carboxyl group and divide it by 2. That isoelectric point is marked smack dab in the middle at 5.97 pH, and that's the point where it's primarily in its zwitterion form. I told you all that was not so bad, so just relax. Now I do have to throw some gasoline on the fire and let you know things are a little different for charged amino acids. Whoa, 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 step back from that ledge. Haha, that reminds me of the "I wish you would step back from that ledge, my friend" song by Third Eye Blind. Pretty dark shit, but god damn it is it catchy. The only difference for charged amino acids is you have to take into consideration the side chains. To find the isoelectric point, for acidic amino acids, it is the pKa of the R group plus the pKa of the carboxyl group over 2. And for the basic amino acids, it is the pKa of the amino group plus the pKa of the R group over 2. See, I told you it's not that bad. So long as you can recognize the amino acids, then it should not be a real issue. If you need to know a shortcut, and honestly that's what this channel is all about, acidic side chains have a low isoelectric point, and basic side chains have a high isoelectric point. As much as I want to say I'm done talking about amino acids, there's one more little bit worth discussing so I can go to sleep at night without having nightmares of amino acids fucking my girlfriend. That would be how these things are grouped up to make proteins, a much more practical thing to learn. Now, if I were to go to transcription right now, I'd probably pull a full Britney Spears and shave my head. Sorry for that reference. I just watched Framing Britney Spears, and I am officially Team Britney. God damn it, is her dad a piece of shit. Anyways, I just needed to get that out of the way and touch on one more thing, that being how peptide bonds are formed. Peptide bonds are formed between the amide group of one amino acid and the carboxyl group of another. 2 amino acids form a dipeptide, 3 amino acids form a tripeptide, and after that, any chain shorter than 20 is an oligopeptide, and any chain longer is a polypeptide. That is as elementary as it's going to get, so if you struggle with the naming system, you'd have better luck working a street corner. Another thing worth noting is that an amino acid chain is written and read starting at the amino terminus, or the N terminus, and ending at the C terminus, or the carboxyl terminus. The formation of peptide bonds is as fucking simple as it's going to get. Water is simply removed as it is formed. A condensation reaction, if you will. Now, I could get into the electrophilic carbonyl-carbon getting attacked by the nucleophilic amide group, but I can feel you falling asleep through the screen. So for now, we're going to stick to the basics. If you make a peptide bond by losing water, let's think about how you break a peptide bond then. Yes, it is as easy as it sounds. You simply add water and get over yourself. There are also enzymes in your body that can catalyze this reaction, and amides can be hydrolyzed by acid or base catalysts. But once again, we're sticking to the basics here, because I know for a fact most of you aren't going to use this to help write your thesis. Well, that finally concludes our discussion on amino acids. Thank the Lord. Now I can finally move on to something a little bit more enjoyable, proteins. Yes, amino acids will return to the fold eventually when we get into transcription, but keep it in your pants because that's not happening until we at least get through proteins, carbs, and lipids. Now, enjoy my masterpiece, and as always, roast me in the comments. See you in Simps next week.